So the first representation method we introduce here uses PCA. The idea is straightforward. Extracting the information contained in a face image is to somehow capture the variation in a collection of faces, and then use the information to encode and compare each individual. One mathematical solution is to find eigenvectors of covariance matrix, or called principal components. These eigenvectors can be thought of as a set of features which together characterize the variation. Each face contributes more or less to each eigenvector, so that we can display the eigenvectors as sort of ghostly face, and they are called eigenfaces. Features in eigenfaces may or may not represent in the original images, so it is less meaningful trying to understand what those features are in eigenfaces. However, by just looking at those pictures, what we can tell is that eigenfaces not only encode facial features, but also the illumination change in the images. With those eigenvectors, we can reconstruct an image from its lower dimensional approximation. Each face is a linear combination of the chosen eigenfaces multiplying corresponding weights, and of course, we need to add the mean face back to get the actual look. In normal PCA, we usually use script plot or proportion of variance explained to select the proper number of PCs. In eigenface analysis, it is better to determine through evaluating those reconstructed images based on whether it is face-like, and also most of the times based on what is your tolerance. In this example, the top 10 eigenvectors are obviously not sufficient for a good reconstruction. The top 50 may already be sufficient to encode important facial features. If we require a very good reconstruction, we will need around 300 eigenvectors. Once we chose the best number of eigenfaces, we can then use their corresponding weights as a new feature vector which represents the original image in the new eigenface space. When an unlabeled face is provided for recognition, we can project it onto the new space and calculate a new set of weights. In sets via visual data mining and machine learning, you can obtain eigenfaces and their weights easily by running proc PCA. Here is a code snippet. We first do a stratified sampling by person ID to partition the data into train and test set, as the way I described earlier. Then, we do principal component analysis on the train set. Underbar part IND underbar is an indicator created from the partitioning step. Proc PCA centers and scales the data by default. Data centering essentially subtracts the mean, but we do not need scaling in this application. N is the chosen number of eigenfaces. Output statement generates a new table which contains principal component weights and the centered values of original inputs. MyCAS library refers to the folder on CAS engine where your data file locates. For more information regarding how to set up CAS server or call VDMML procedures, please contact support.sas.com. The second representation method is called LBP, Local Binary Pattern. LBP also extracts characteristic features of a face, but it's fundamentally different from eigenfaces. Eigenface is appearance-based, so it analyzes the appearance variation from the whole face. LBP instead generates binary code to describe local texture patterns in a small neighborhood. And so, it well summarizes local spatial structures. There are several variants of LBP. The original LBP operator works in a 3x3 neighborhood. For each pixel, calculate a binary transformation of its neighbors using the grayscale value of the center pixel as threshold. For example, if a neighbor pixel has value higher than or the same as the center pixel, it is 1. Otherwise, it is 0. In the next step, we need to obtain one representation of the neighborhood information. So we concatenate the binary codes into one binary string and then convert the binary string to a decimal value. This value is called LBP value. It doesn't matter which direction to rotate, either clockwise or counterclockwise, but once it is set, it needs to be consistent across all the neighborhoods. The starting point of the binary string is chosen by minimizing the decimal value after conversion. There are other ways to determine the LBP value, and the popular one is called uniform LBP, which constructs a binary string containing at most 2 bitwise transitions. One bitwise transition refers to a change in the binary code from 0 to 1 or vice versa. We can do such conversion and calculate the LBP value for each pixel in an image. There are some good reasons to use LBP. First, as I mentioned, it captures local texture information and it can detect important local textures like spots, lines, corners, and edges. Second, LBP is not sensitive to illumination change because it depends on the relative grayscale values of center pixels. Once the LBP value is calculated for each pixel, the image is then represented by a new feature vector. We call it a LBP array. Similar to eigenface, LBP array also retains some sort of face type. Then in the last step of the original LBP algorithm, a histogram is constructed on the LBP array. Consider a 3 by 3 neighborhood. There are 2 to the power of 8 possible patterns, and so a LBP histogram can have 256 bins. This algorithm can be further improved by segmenting an image into smaller blocks. A LBP histogram is then constructed on each block. The final LBP features concatenates histograms from all the blocks. Our method is different. We work on the LBP arrays directly instead of the histograms. We also divide images into blocks and build a classification model within blocks for the same location. Each model now only sees part of the whole image, so it is considered as a weak learner. For example, if we divide the image all into 5 by 5 blocks, we then yield 25 weak learners, and the final classification is done by majority voting of all the weak learners. SAS Via provides open APIs so that SAS Analytics is accessible to popular languages like Python. We implemented our modified LBP method in Python. The first thing we need to do is to read each image file into a list of intensity values, and the images can be stored in folders and subfolders. Then we call a LBP transformation function to calculate LBP values for each pixel. They are further divided into 25 blocks and rearranged to 25 LBP arrays. We built neural network blockwise as classifiers. We start with loading the action set neural net in CAS. The ANN train action creates and trains artificial neural network for classification. Some important parameters we can specify in the action are like network structure, number of hidden units, and some optimization options too. Table and valid table parameters specify train and valid dataset. The score action provides the posterior probability of a face being classified to a class. We can build individual classifier on each of the 25 segments and identify a person by taking the majority of the votes. Please check out the GitHub repository to find examples in this demo.